Hey guys, yeah, let's do another lesson in this new unit. So today we're going to talk about fields. So we need to define a field as a property of space around a mass, an electric charge, or a magnet that causes another mass, an electric charge, or magnet introduced to this region to experience a force. Compare interaction with static electric charges, and compare basic properties of vector fields, and draw diagrams to represent them. Okay, so first thing we're going to talk about is one we're most familiar with, gravitational field. So a gravitational field is created by any object with mass. So any object with mass creates a gravitational field. And a field is a 3D area of influence around an object. So when you place the correct object in that field, it'll experience a force. So here's Earth. So Earth is very massive, and it creates a very large gravitational field. So the correct object I can place in this field is another object with mass. So if I place an object with mass out here, it'll start to get pulled into Earth and fall into Earth's atmosphere, right? So we can represent Earth's gravitational field with gravitational field lines. So gravitational field lines just show which direction an object would go if we placed it at that location. So if I placed an object here, it would go towards Earth. If I placed an object here, it would go towards Earth. If I placed an object here, it would go towards Earth. So with Earth and a gravitational field, it's really nice and easy. Our gravitational field lines always go towards our Earth. Okay. So people are like, yeah, that's pretty straightforward, but it's not that straightforward. It's actually kind of a confusing idea because people mix up this idea of field and this idea of force. Forces and fields are different things. So this field around Earth always exists, but if you place the right object in it, it'll experience a force. So I have a little analogy for this. So here is oiled up buff dudes, and your parents are going to walk in right now and be like, I thought you were doing school and not looking at oiled up buff dudes again. Can you quit it? But anyways, let's look at these oiled up buff dudes. So these oiled up buff dudes create a oiled up buff dude field. And we can send an object through this oiled up buff dude field. So say you are a person that really likes these oiled up buff dudes, right? So this is someone who's into it, they like their body, maybe they strive to achieve that body. Like, look at those abs, those are pretty impressive. Look at his eyes, so nice. Anyways, so this person, let's say, has a positive feeling towards these oiled up buff dudes. So as they go into this oiled up buff dude field, they're going to experience a force, and they're going to want to touch those abs, and they're going to want to, oh yeah, oh yeah, oh yeah, is what they're going to want to do. They're going to experience a force in that oiled up buff guy field. But let's take a different object. Let's take someone else who isn't really into these oiled up buff dudes, kind of feels like it's body shaming, and they worked way too hard. They prefer a dad bod type situation. So this person walks through. So are they going to experience a force? No, they're just going to walk through because they don't care about these oiled up buff dudes. So in both situations, the oiled up buff dude field exists, right? This is the oiled up buff dude field in between here. But if you're not into the oiled up buff dudes, you don't experience a force. But if you are, then you do experience a force. So you can see how a field and a force are different things, right? They act differently. If a field exists, an object can experience a force. It doesn't have to experience a force, and that's what we're going to learn. Okay, so electric field. So if a mass causes a gravitational field, what causes an electric field? Well, anything with charged, anything that's charged up. If I have extra electrons, or if I'm lacking electrons. So if I'm lacking electrons, I'll be positive. If I'm missing some, and if I'm have extra electrons, I'm negatively charged. So what would be affected by an electric field? Well, something with charge, right? If I'm a positive object, right, I'm going to be attracted to this negative charge, and I'm going to be repelled from that positive charge. So other objects with charge are affected by electric fields. And what happens to your electric field if you go further away from it? well, it gets weaker. Right? If I'm further away, I'm not going to be as attracted or as repelled. So here, just like the oiled up buff dude field, we send an object through. So we need to give a direction to this field. So let me go back. So with Earth's gravitational field, it was always towards the Earth. So we need to do the same thing with charged up objects. The tricky thing is that we don't ever have negative mass or positive mass. We just have mass or we don't have mass, right? So we can have a positive object and a negative object. So if I have a negative object, I am going to go to the positive side. If I have a positive object, I'm going to go to the negative side. So which way is our electric field actually going to be? So what scientists had to do is they had to pick, and they had to choose someone to be our test object. So the person that they chose to be their test object was Pedro here. Hi, I am Pedro, and I determine the direction of electric fields. Okay, so if I stick Pedro close to this positive charge. Oh, and one thing I should explain about Pedro is he's really positive. Yes, very positive. Always positive all the time. Pedro! So he's very positive. So I stick him by this positive charge. What Pedro's going to do is Pedro doesn't need to be by any other positive things. He's going to go away. And no matter where I put him, Pedro will always be repelled by this positive charge. And if I put a negative charge there, well, Pedro wants to make them feel better, so he's going to go towards that negative charge, right? No matter where we put him, he's always going to go by that negative charge. And if we had a situation where we had a positive side and a negative side, like this, and we stick Pedro in here, well, Pedro's always going to go towards the negative side, and that's how we draw our field in. We use Pedro to help us, and Pedro, the positive test charge, will tell us what direction our charge or our field is going. So to find the direction of electric fields, you just ask yourself, what would Pedro do? And the direction of electric field is always the direction of positive test charge, so Pedro would move when placed in that field. Okay, magnetic fields. Well, what causes a magnetic field? Well, that's easy. A magnet. A magnet causes a magnetic field. And what's affected by magnetic fields? So there's a few things. So other magnets are affected by it. A compass, like a compass finding direction, and also metals. Metals are affected by it. Metals such as iron are affected by magnetic fields. So we're supposed to do an activity in class, but we can't really do it, so I will do the activity for you. Oops, wrong one. Right here. So a compass seems like it's different from a magnet, but it's not different from a magnet. A compass is just a magnet that's allowed to move around. So you can see the red side of this is north, and the red side of this is north as well. The white side is south, the white side is south. So just like with charges, positives, two positives would repel, and a positive and a negative would attract. Right? With a compass, south is attracted to north, and north is attracted to south. Right? So if we place this compass at different points, we can see the direction of our compass needle changes. So the way we determine direction with of a bar magnet like this is whatever way the north is pointed in the compass, right? So you can see when I put it by the north end of my compass points away. When I put it by my south end, it points towards it. But when I put it in between, it's both repelled by this and attracted by this, so it kind of goes to the side. So you can see that it follows this pattern, kind of like this pattern we see in the background here, right? On the top and the bottom, it follows this pattern. So what we end up seeing is our magnetic field runs in these loops, like this. So it follows that pattern, and it always is trying to go away from the north and towards the south, but following this loop sort of pattern, right? Same thing on the bottom, away from the north and towards the south. So this is the direction that a magnetic field is around a bar magnet. So the Earth is kind of like a giant bar magnet, and compasses work like iron filings, and they try to orient themselves with the Earth's magnetic field. However, the north pole of the magnet should always seek the south pole of another magnet. So what's weird is that, let me open up a simulation. Let me show planet Earth here. So when our compass points upwards like that, we say, oh, up is north, but north should be seeking south. So when they made which end is north and which end is south, they actually had it backwards, right? Because our north pole of our compass seeks the south pole. So what that means is that geographic north is actually magnetic south, and geographic south is magnetic north. So that's a little bit weird. So this is the north pole, but it's actually magnetic south, and this is the south pole, but it's actually magnetic north. So it's just a little bit backwards. So gravitational forces always attract, but with magnets, likes repel and opposites attract, right? So if I put two positive charges by each other, they would repel. If I put two negative charges by each other, they would repel. But if I put a positive and a negative by each other, they would attract. Same thing with bar magnets. Bar magnets always have a north and a south. So, oops, sorry. If I had a north and a south right here, then these bar magnets would repel because I have north and north. But if I set them up, so it's like north and south, and north and south, well, now the north attracts the south, so these ones would attract. So this is the reason why the northern lights, sorry, I deleted this slide, but I think I had other stuff in here, is that there's charged particles throughout space, and these charged particles are deflected by Earth's magnetic field, and they move in a circle, and they create bright light. Anyways, so that's all you really need to know is to draw in field lines. So we're going to do a board question here. So just pause the video, try it yourself, and then I'll show you the answer. So pause it now, or pause it now. So draw the magnetic field around a bar magnet. So you have to label a north and a south side, and they go in loops like that. So the magnetic field always goes from north to south. From north, away from the north, towards the south. Okay, hopefully you drew that. Okay, draw it around Earth's moon. So pause the video. So Earth's moon is a mass, so it has a gravitational field, but it doesn't have a magnetic field. It's not like Earth. Earth has a magnetic field around it, but the moon is like a dead rock. It doesn't, so it just has a gravitational field, so it will always point towards it. And if we had a positively charged sphere, so pause it, try it on your own. So as positive, then Pedro would move away. So Pedro tells us that we move away from it. And if I have a negatively charged balloon, well, it's charged up, Pedro would move towards that negative charge. So we would draw this towards. Okay. And our last one, two charged plates. So this is an electric field. So I have placed Pedro in here, and Pedro would go towards the negative. So it'd just be lined straight down towards the negative inside. And we'd only have to worry about inside. That's what it would look like. Okay. So I'll post an assignment, and that's it for this lesson.